Well, my dear participants, today I am going to talk about the extension on center limit theorem when parent is binomial distribution with probability p is equal to 0.5. So, when p is equal to 0.5, what happens about CLT, about central limit theorem? So, see, I have written a command in R. See, it is 1000 sample means of size 10 from binomial. So, x bar b10 is equal to replicate 1000 times, it has to be repeated, and expression is it will generate the mean, and mean is actually based on the R binom, that is random observations from binomial distribution with n is equal to 10 and with n is equal to 10, size is equal to 10 and p is equal to 0.5. So, it will take a random sample of size 10 from binomial distribution every time and it will compute its mean. So, and this process will be repeated 1000 times. So, as a result, with binomial probability p, so mean is 5.008 and actually this mean is nothing but it is NP, mean is equal to NP, n the size and p is the parameter. So, n into 10, that is 10 into 0.5, so that will be 5. So, this is the simulated means is nothing but it is 5.0086. So, and the simulated SD is nothing but it should be equal to 0.5 because NP, it is square root of NP into 1 minus p divided by n. So, n is 10 and p is 0.5. So, 10 into 0.5 into 0.5 divided by 10. So, it becomes 0.5, 0.492, which is equivalent to 0.5. Now, we are making a histogram on the basis of this simulated data. Hist x bar 10, this histogram is based on 1000 observations, 1000 sample mean generated by the process, by the function replicate. So, these are the 1000 random observations of sample mean and prob is equal to true, y lim is equal to 0.08. So, this way, and then we are adding a curve. So, this histogram is made on the basis of the simulated data and this curve is exact curve. So, exact curve we are adding and that is d norm. Actually it is an approximation because we are talking of we are trying to approximate the sample means approaching to normal distribution. So, that is why this simulated data, which is on the basis of which we are making this histogram, is we are trying to approximate this by the normal distribution because of center limit effect. So, here d norm x mean is equal to 10 into 0.5, that is 5, and d SD is equal to SQRT 10 into 0.5 into 0.5 divided by 10, add is equal to true. So, see here there is good agreement between the simulated data and exact curve. There is good agreement between the simulated data and exact curve. So, that means it is very good result of CLT because p is equal to 0.5. Comparison of exact and approximate sampling distribution of sample mean 10 is equal to 0.5 from binomial. But see what happens when p is equal to 0.1. So, p lies between 0 and 1. So, we shall begin with p is equal to 0.5 when it lies in the mid. Now, in the left extreme we are going what happens, it is what happens when p is equal to 0.5. See, Here we have changed x bar 10, x bar 10, see replicate, 1000 times it is being replicated. Expression is equal to mean R binomial n is equal to 10, size is equal to 10, but p is equal to not 0.5, p is equal to 0.1. And now mean is actually 1.00, so mean is very close, and SD is also 0.30. Now see what happens about the histogram. Hist x bar, we are making histogram on the basis of simulated data. So this is the histogram based on simulated data, and here we are adding normal curve on this histogram. But see what happens. D curve D norm x mean is equal to 10 into 0.1, SD is equal to SQRT 0.1 into 0.9 divided by 10, add is equal to true. So here you see the histogram shows right skewness. It is skewed in the right, whereas this curve, so the curve is not matching fully with the distribution. So here the approximation, the center limit theorem does not work well in the case of 0.1, p is equal to 0.1. As see here, it is not matching, it is not matching with the extremes, whereas in the earlier case it is matching, it is matching. So with p is equal to 0.5, it gives good approximation, whereas in the case of 0.1, p is equal to 0.1, it is not as good as in the case of 0.5. Now it is right skewed distribution, whereas normal is symmetric. So what happens CLT when p is equal to 0.5 with binomial? P is equal to 0.9. See, we again repeat the same process with p is equal to 0.9 and see what happens. Again we are making the histogram and we are doing all that. The process hist x bar, see, mean is 8.97. So 0.9 into 10 is actually 0.9 into 10, so it should be 9. So 8.978, it is almost 9, and SD 0.30, so it should be around 0.30. And x hist x bar, prob is equal to true, y lim is equal to C 0 1.3, and curve D norm x mean is equal to 10 into 0.9, standard deviation is equal to 10 into p 0.9 into 1 minus p 0.1 divided by 10, add is equal to true. Here in this situation, it is again skewed, but it is left, it is skewed in the left, not in the right, when p is equal to 0.9. So this is the effect of choice of the p. We can try for some other values of p, like if we have 0.01, see what happens. So we can go on, we can generate these things. So here we have written the command and we can run these commands. See, this is the output, this is the output. Here agreement between the histogram and curve is very close because it is symmetric. But when we go for p is equal to 0.1, see what happens. See, it is not in good agreement because it is right skewed. Now when P is equal to 0.9, see what happens, it is left skewed. So here skewness is not good. We can change these by making some other options. Say for example, if we have P is equal to 0.01, see what happens. If we have P is equal to 0.01, see what happens when P is equal to 0.01. So here we have to make changes, like it is 0.01 and replicate. So here we have to make changes like it is 0.01 and so here it is all right, and see here it is 0.01 and here also it is 0.01 and here it should be it should be 1 minus 0.01, so it is 0.99. So it should be 0.99. Now see what happens when we run this. See here, picture is not good. Picture is not good because of keeping in the extreme. Here it is highly right skewed, so this effect is there. Similarly, if we keep this 0.25 and here also, so we should make changes 0.25. So here I have to change 0.25 and here it should be 0.25 and here it should be 1 minus 0.25, so it should be 0.75. Now if we run this, see what happens. So here it is P is equal to 0.25. Now we run, see here situation is again right skewed distribution we are getting, but situation has been improved. Situation has been improved. If we are keeping 0.50, then it is the best situation. So this is all about how P varies and this affects. But if we keep, say for example, sample size, say for example instead of 10, suppose we increase up to 100, increase up to 100 sample size. So see what happens. $100. So here it should be 100 and rest are the same. See here 100 into 0.75. So situation is somewhat improved. We have to increase the limit, we have to increase the y lim, and then certainly it will work then. So this is the effect of choosing. Now when parent is Poisson, what will be the effect of central limit theorem? So first I would like to go into the PDF, and there I would like to display from here. When parent is Poisson with lambda is equal to 20. If lambda is equal to 20, see what happens, because there is a theory that if lambda, theory I am quoting from the book of Alan Agresti, Categorical Data Analysis, in which Agresti discusses the Poisson approximation to normal, and he says that if your parameter lambda is greater than 6 or 7, the distribution can be approximated well by a normal distribution. So here we are taking Poisson with lambda is equal to 20 and see what happens. Then we are writing x bar 10, replicate 1000, expression mean, R Poisson, n is equal to 10 and lambda is equal to 20 and mean x bar. So its mean is 20, so it is well close, and SD is 20 by n, SQRT 20 by n, so it is 1.4. It is 1.4. So it is well closed. And when we make a histogram, hist x bar 10, prob is equal to true, y is equal to this thing, and curve d norm mean is equal to 20, SD is equal to 20 by 10, and add is equal to 2. See here, when lambda is equal to true, it is very close to normal distribution. Lambda is equal to 20. It is very close. This histogram is based on the simulated data, whereas this normal curve is because of the normality, because of the CLT, and they are in close agreement. So that means it works well. Now I would like to run these things on here, Poisson when lambda is equal to 20. So these are the commands I have written, and we can run these commands, and this is the output. See, they are in good agreement. CLT works well because lambda is equal to 20. But see what happens when lambda is equal to 2 only. Lambda is equal to 2 only. What happens when lambda is equal to 2? So I would like to go there. What happens when lambda is equal to 2? This is the lambda is equal to 2 situation. With lambda is equal to 2, because it is less than 6. It is less than 6. So what we expect? We don't expect good approximation. So central limit theorem does not work well here. So what we have done, that we have simulated 1000 observations from the mean. We are computing mean. We are computing 1000 means, and mean is based on the R Poisson random observations. 10 observations we are simulating from Poisson distribution with lambda is equal to 2, and then we are computing mean, and we want to seek the performance of the mean as we are talking in terms of. So here mean should be, lambda should be 2. So it is 1.988, which is very close to 2. And SD should be 2 by n. So it is 0.42, which is very close to 2. Very close to 2 by 10. 2 by 10. Now we are making a histogram. Histogram, prob is equal to true, y lim, and curve d norm, mean is equal to 2, SD is equal to 2 by 10, add is equal to 2. See here, the agreement between the normal distribution and the histogram simulated by the replicate function, they are not in good agreement. So that means Here center limit theorem does not work well when lambda is smaller than 6, that is 2, because you know this is right skewed distribution and it is not matching with the normal distribution. So we can run these commands. We can run these commands here. These are the commands written in the text in the RStudio, and we just click and we are getting the result. See, here they are not matching because lambda is equal to 2. So we can think of some other values of lambda. But I am going to talk about another distribution, and that is chi-square distribution with k degrees of freedom. So here chi-square distribution with k degrees of freedom, I am going to talk chi-square with k degrees of freedom, chi-square distribution with k degrees of freedom. See, it is a well-known fact that if z follows normal 0, 1, then z square follows chi-square with 1 degree of freedom. That is chi-square distribution with single degree of freedom. So this is the sampling distribution. This is the sampling, chi-square is the sampling distribution, because z square is a statistic. So now chi-sq1 we are simulating data, replicate 1000 times. We want to compute what? We want to compute expression is equal to R norm 1 raised power 2. So what we are doing, R norm means it will generate one z value from the standard normal distribution, and then we are making a square of that. So it is z square, it is z square, and computation of z square is being repeated 1000 times. So we have 1000 values, and then we are making histogram, and prob is equal to true, y lim is equal to this, and x lim is equal to 0, 8, curve d chi sq x df is equal to 1. Actually with curve we always have x here. Whenever we use curve command, it must be x here to represent on x axis. df is equal to 1, add is equal to true. So now if we look into the graphics, this is the histogram based on simulated data, and this chi-square distribution with single degree of freedom is exact curve. Both are matching together, both are in good agreement. So this shows that the simulation made in this situation is actually from chi-square distribution, because we are making this histogram on simulated data, whereas curve is exact curve, but both are matching. So that means our simulation is very good, and we can get these commands by just clicking here. See, we just run. See, this is the histogram and this is the curve. So they are both in good agreement. Now I would like to go on. If this is a well-known result that if we can define chi-square with 5 degrees of freedom is defined as if zi is normal 0, 1, I is equal to 1 is to 5, then summation zi square, I runs from 1 to 5, follows chi-square with 5 degrees of freedom. This fact can be implemented using R commands, and these are the commands. Chi-sq 5 is equal to replicate, 1000 observations are being simulated, and they are nothing but expression is equal to sum. So this is sum and this is z square with, so it generates 5 observations from standard normal, and then it makes square and gets sum. Say and then we are making a histogram, and then we are adding a curve, and these two are matching together. So there is excellent agreement between the two. And if I go here, I can show you the command here, sum R norm 5. I am trying to explain this command R norm 5. R norm 5. It is nothing but it will generate 5 observations from normal 0, 1. So these are the 5 observations from normal 0, 1. So what we are doing? We are making a square of each of these. We are making a square of each of these. So these are the squares. And then we are getting sum of these. So this is nothing but summation zi square in the first replicate, and this process is to be repeated how many times? 1000 times. So that's why this expression sum R norm, and 1000 times it is being repeated. So we have 1000 chi-square 5 deviates, and this is the histogram based on that, and this is the normal curve d chi-sq x. We are writing x here because it comes with curve. Whenever we write curve here always it should be x. df is equal to 5, add is equal to true. And see, these are in good agreement. This histogram is made on simulated data, whereas this curve is exact chi-square curve. It is evident from above figure that simulated and exact curve are very close, depicting the fact that both represent the same distribution. Now, I can talk about when the degree of freedom becomes 30, then what will happen. So that I will continue in my next lecture.